My name is Anirudha. I work for Bloomberg as their data platform lead. Primarily, the products that my team supports are Bloomberg Cloud Data Flow, which is an ingestion pipeline, and which has a heavily, tightly integrated service as a software as a service framework into providing SQL as a service built around HBase. And that's primarily why we are here today. We mostly support medium data and big data applications. And a couple of years ago, these were a rarity. But nowadays, as more and more teams and more data has been generated, these applications are no longer a rarity. These are kind of the norm. Everything is kind of big data and medium data. And what we want to go towards right now and focus on is, we had these Snowflake implementations, very custom specialized implementations for use cases. What we are going towards and the goals and objective for my teams are to provide repeatable infrastructures built around a technology stack, which can support every single nuance of the life cycle and improve the developer experience for teams using these technologies. Today, we'll talk primarily about Phoenix, what it is, a brief description, and we'll also jump into our journey into how we have added some features into Phoenix. What has been possible for us because of Phoenix and where we want to take it going ahead. So, as many of you already know, Bloomberg is the leading data and analytics provider for the global financial markets. Anything and everything related to finance and what affects a financial entity or financial outcome is being monitored and tracked by us. Oops. Okay, we're good. No. Okay, perfect. Okay. So the main objective that I'm trying to achieve over here is we have to build for repeatable architectures. And what it really means for us as a company is we have different types of data assets that can be visualized in various different ways. For example, geospatial data, which allows us, our users, to get and analyze where are all the ships in all the oceans of the world. What are they carrying? What are the weather anomalies alongside of it? So can this commodity reach a particular port correctly on time? All the news wires coming through major news bureaus over the world, how can we apply real-time streams to aggregate them in a meaningful way? And also provide various other use cases which do high-level aggregation analytics or provide drill-down views. So with most of these applications being developed to improve the developer experience, and what we have found with applications working with HBase primarily are the data model that we set out with. The defining of the data model is a very sort of a historic term for a project. And that data model is kind of thought about, this is the best we have done right now. And there will be minor changes, but not much. But every single application that we have worked with, things change, and nobody can decide what a final data model should be. Some of the main challenges are the data model regularly changes, and things that we have to support is backward and forward compatibility. We can never build applications without a support for backward forward compatibility. On the other hand, even though your data model changes, the users who are going to use your system, they might be on older APIs, they might switch to newer systems, and you have multiple users using the same databases. How do we support these backward forward query patterns from them? And a data set that you have been designed for is going to be queried across multiple different parameters, or you can add different query predicates on top of it. How do you make sure that every access pattern works? What I'm getting at over here is really, can you ever define a key for you that always fits that use case? Will your key needs changes overall in the lifetime of the project? So the goal that the data infrastructure team and our teams have is really to make these structures repeatable and to make usage of modern data infrastructure and the developer experience around it much more simpler and more resilient at the same time. So for everybody else who doesn't know what Phoenix is, let me try to define this and how I would like to define it for myself. For me, if you are building applications around HBase, Phoenix is really those set of recipes. All the recipes for using HBase in a more efficient manner, or good set of recipes for using HBase, they're kind of combined together. And this is what is Phoenix, and this is provided to you over a SQL-ish grammar. It is SQL, it is ANSI compliant, and it has also changed and evolved some things which are not standard SQL. So it's what we want it to be. Do we have wide column support over it? Maybe that's the right thing to do, and maybe we'll add that. So things like this we have to always think about. So if you're building an application, would you like to use Phoenix, and does it serve all your use cases? Or would you choose not using Phoenix because of a small feature you don't have? And now there's a choice that you have to make. Can you build it, contribute it, or do you just go off of it? We've taken the path that it's much more wiser to build it and contribute it, or rather than going away from it, to achieve repeatable success. So some of the features in Phoenix that I would like to point out that are not more common and thought about are user-defined push-down functions. So you can write some functions which can operate on your data and push down for execution. Secondary indices everybody is aware of. Statistics collections are used heavily for optimizations on how queries can be distributed for max parallelism and throughput. For developer experience, how many of us really write SQL statements and combine them? A lot of frameworks use ORM libraries and Fluent libraries. There are frameworks available for ORM manipulations over Phoenix datasets right now, which are contributed by others. JDBC and ODBC support brings you standard environments. Now you can plug in other tool chains and also you reuse the same data sets and get multiple views for analytics or to get your data out of the system. Also at the same time, other projects in the community like Spark, Kafka, MapReduce, and there are many other projects which have been having direct integrations into the Phoenix ecosystem. So all this going on together is kind of a good thing that Phoenix fits in right for designing your big data infrastructure and architectures around. And the most important part of this is the community. It's a pretty active and helpful community. The rate of feature releases, how bug fixes, comments, new issues have been going on is always positive. And that's the key part that we were interested in. It started from a small project with one company, but now it is not that anymore. There are so many more companies contributing into it, which gives us a strong ecosystem and confidence that we can keep on adding more and more features into this. So this is some of the ongoing work that we have been involved on. And this is primarily towards projects like Apache Calcite. This is a future project. We've been involved in fixing bugs, adding small issues, and helping out however we can. We inside our company also are planning to run distributed tests. We'll be talking more about the project that we're pushing out towards this tomorrow at PhoenixCon, but we want to make sure the same HBase distributed test suite that everybody else knows over here, how can we port that over? So we have ported a couple of tests, the test running framework and the big linked list tests into Phoenix, so we can run it on a distributed cluster. That gives us more and more confidence, and we will add more and more tests going ahead and porting these things over. Multi-DC replication is one major thing that we want to achieve, and how can we do that efficiently? And we've been constantly working on these pieces. And the second piece, which is the later part of the discussion, is cursors. So the key motivation for cursors is how we involve ourselves with dealing with data sets inside our company. We have tabular views, aggregations, which can be used page by page fashion. That is mostly a lot of our use case. Now, what happens currently in Phoenix, if you start paging down deeper and deeper, the time it takes to retrieve becomes slower. And this is the main problem that we're trying to fix. The cursors implementation goes one step ahead towards getting a clean developer experience to paging, but there are also still some more work required over here to get the performance in place for deep paging. Deep paging is what our end goal is with our cursor implementation. And this is a journey that we have started. It's halfway in, some pieces are still remaining, but this is what makes it better for us. Did we reinvent the entire wheel? And we could have done it in HBase straight and got this one feature, but for an entire ecosystem, and to make sure we enable this interface to our developer community inside the company to provide a clean developer experience, provide JDBC wrappers, provides metrics, monitoring, the entire framework. It can be done once in a repeatable fashion. I'll hand it over to my colleague Biju. He's going to go more into the implementation of cursors, a deep dive into if you want to choose to add a feature into HBase and Phoenix and expose it over Phoenix, how would you take that journey for yourself?
Thank you, Ani. Good afternoon, all. Hope I can keep you awake for the rest of the talk, which is close to the coffee time or coffee break. And also, before I start, I need to thank Ankit, who is the committer in the Phoenix project, who has been helping us and guiding us all the way through. And also Gabriel from MIT, who did an initial implementation of these cursors when he was with Bloomberg, maybe last year, I assume. And last but not the least, the Phoenix community, and especially James for all the comments and feedback you provided during this work. Before we go further or talk about the cursor implementations, what we have done so far, want to set the stage by talking through Phoenix architecture and then what happens when a query gets executed inside Phoenix. I hope I'll do a correct job. If there's any mistakes, we can correct it afterwards, James. Being HBase professionals or people who have been using HBase, I'm pretty sure looking at this diagram, you can tell that somebody is trying to represent HBase at that 1 million feet level. So us with HBase and in all these distributed frameworks, which follow a secret little first principle called it gets two to tango. Phoenix also has got two components. One is the client component as well as the, oops. Oh, right there. Sorry. Okay, Phoenix has a client component and a server component. They are all packaged in jar files. So if you want to enable Phoenix on a HBase cluster, what you do is you install the HBase, the server component or the server jar in all the region servers of the cluster and restart the region servers. So the server components primarily consists of a set of coprocessors and endpoint implementations. So the main idea is to convey what components Phoenix leverages or what components of HBase the Phoenix leverages to give a user an experience, a SQL interface for the users. So what are coprocessors? Coprocessors are custom code, which enables users to be able to run custom code within HBase, primarily on various trigger points. So when I say trigger points, consider a table put. That can be a trigger point. Like we can make custom code to run when a put happens or a get happens, or if a region server starts or a region server stops, or whether there's an action taken on a metadata in a master. So there are flavors, a set of different flavors of coprocessors, namely region level coprocessors, or region server level coprocessors, or the coprocessor which can run on the master, or coprocessors which can run when there's an action taken on a val, which is right ahead log. So all these coprocessors all get attached to all the tables created by Phoenix on HBase. So also in coprocessors, you can define the sequence in which this coprocessor has to execute. So we'll come back and see how it all fits together when we look at the query execution, how these coprocessors play a role to be able to serve the data back to the client. The second set of things which is involved on the Phoenix server is a set of tables called the system tables. One example being the catalog table. what it does is it stores all the Phoenix related objects or metadata related to the Phoenix objects created within HBase. So when you issue a statement like create table, the system catalog table would contain the table name, the columns, the data types, etc., so that Phoenix can use that data to be able to service the queries. Okay, so that's on the server side. Let's look at the client side. The client side, the client library or the client jar or the client code satisfies or does multiple functions. So if you look at here, it does the connection management, it does the authentication. In our case, in Bloomberg, we have all the HBase servers secured. So authentication is an important piece, so which is taken care by the Phoenix client. But if you look at it, behind the scenes, it depends on the HBase client libraries. The Phoenix client also does SQL parsing. The SQL parsing depends on Antler. What happens is when you have in Phoenix, the SQL's grammar is defined, and then Antler is used to generate the parser code, which in turn is used within Phoenix client. The Phoenix client also does the query optimization, rewrite, query plan generation, and also it helps with the transaction management. Currently, what happens is the query rewriting and optimization and the query plan generation, it's all done using either hints parsed by the users to the SQL query or using the static rules, what is defined in the Phoenix code. And there's a parallel project currently going on. I think Ani briefly touched on that. The Phoenix project is moving from Antler to Calcite, which provides the cost-based optimization to query plan generation. So now we know that we know on a high level, at least a million feet level, the architecture of or what's involved in between the client side and the server side of Phoenix. Let's take a look at what happens when queries gets executed. So it's no surprise that any JDBC application, these are the calls which needs to be made to run a query. And the query here is boring and simple. I think Sudarshan suggested let's do a much more challenging query here, but I want to keep it simple so that it's easy to explain to get the concept out. So typically what does we make a connection, we prepare a statement, then you'd execute the statement and you get a result set, and the application goes to the iteration, iterate to the result set, and then does a close of the result set. So it's plain and simple from the user perspective, but we can see what it happens behind the scenes. So for each of the statement, Phoenix client does the connection, like for example, connecting the HBase as part of the process. It also do the authentication. Then comes the execution, the SQL parsing. The SQL parsing, it validates the SQL against the grammar to make sure that there's no syntax error. Once that is complete, then then Phoenix client talks to the server to get the metadata to make sure that all the objects referenced within the SQL statement is available on the server side so that the query can be satisfied. Once the validation is complete, then it generates the query plan, and then the query plan optimization is done. And once the optimization is done, or the correct or the suitable query plan is generated, then an iterator is formed behind the scenes. So for example, in the select statement, which is the simple and the boring select statement, what happens is it creates a scan iterator, which nothing but, if you think about it in the HBase terms, it's just a scanner behind the scenes. So once that is created, and also the result iterator, along with the result iterator, there'll be a new object called a projector iterator. A projector object. Projection means like, if in a select statement, if you have 10 rows, 10 columns in a table, if you're only selecting 2 columns, so that's the projection for that SQL statement. So there's a projection object is created, and then combined using the iterator and the projection object, result set is generated and passed back to the client. So the result iterator, the result set can be iterated by the client to satisfy the query, and at the end, it gets closed. That means behind the scenes, the iterator gets closed and the scanner object gets closed behind the scenes in HBase as well. So this is behind the scene what happens when a query get executed. In order to support the query, the server side, if you look at it, when the metadata request is made, it talks to the endpoint implementation. Endpoint implementation, we talked about coprocessors, which are custom code, which facilitates or which helps users to write custom code on trigger points. But endpoint implementation just gives you an option to run a custom code and which can be directly called from the HBase client side. So in the case of a metadata request, it talks to the metadata endpoint implementation, which in turn talks to the or retrieves the data from system catalog table and responds back. On a read request, like an select query, the queries, depending upon the query type, say, for example, you have a select query which says select something from table, count a column and group by something, then the grouped aggregate RO, here in this case short term for region observer coprocessor, will be used, and the response will be sent back, and the Phoenix client would work on the aggregation on the clients and whatever it has need to do. So what I'm saying is, on the back end, these coprocessors will be used for various type of queries which has been issued by the client. And on the write side or the mutation side, as you would know, in Phoenix you have indexes, and in order to keep the data between the user table and the index table to be in sync, the indexer coprocessor will be used. So this is the whole high-level architecture, as well as the sequence of steps, what happens behind the scenes to satisfy the query execution. So let's move on quickly to understand what cursor is, because this gives a good background to understand what the cursor implementation is. So from the requirement perspective, the requirement was pretty simple and straightforward. Users or the client should be able to get a set of data to which they can traverse backwards and forwards, and the data should be consistent. That means they should be able to get a snapshot view of the data during the processing of traversal between back and forth. And at this time, as Ani was pointing out, most of the use cases are to be able to satisfy queries. So if you're familiar with SQL standards or been working with cursors with other databases, it's more than just the queries. It allows you to in-place updates, mutations, and whatnot. But our requirement is much more confined, and that's to satisfy the construct of cursors was a suitable choice. So to take an example and contradict with what happens in a normal result set, a declare cursor would a user can declare a cursor for us any query statement, again the boring query here, and then open the cursor, and the users can do a fetch. It returns back a result set object, so they can use it to iterate to the result set. And then if they can issue another fetch statement, that means go backwards with a fetch prior. So, and then do whatever they want to do, and then close the cursor. So in this case, if you have 10 rows initially in the 10, so 1 to 10, when you do a fetch fire, then it goes from 10 to 6 backwards. So they can traverse back and forth. So that's the idea here. Implementation. So there were discussions which was made in this ticket, that is Phoenix 2606. And the first implementation of Phoenix, the cursor was implemented using row value constructors, which is supported in Phoenix. In the interest of time, I'm just going to skip that one, and then just briefly say that the row value construction implementation was much more complex and unmaintainable. And then the suggestion, when we discussed with the community, I think Ankit and James and all came back and said, why don't we wrap around the current results at which we already support for all the queries? So that's the current implementation, what we are done. So again, similar to the JDBC commands or the API interface, we're using the JDBC API interface, you can see what happens, how to code a cursor and how to navigate through the results that are returned by the cursor. So again, declare, open, fetch, and then do the iteration to the result set, close the cursor, and pretty much done with it. So now let's look at how it's implemented behind the scenes, like how we looked at the query implementation. So I'm just going to skip, I skipped some of the steps what was already been discussed. So in the case of declare cursor, what happens is the cursor, this query parser parses the statement and identifies the name of the cursor and the SQL statement. And then the SQL segment is used to, like what other steps went through the normal query processing. It gets, again, parsed, compiled, query plan generated, and it creates an iterator. So before even going, the plan is generated when we do the declare cluster statement. And what we do is we take that plan and create a wrapper object and then store in a map with the cursor name being the key for the map. So the next time when the same application comes back and issues an open cursor statement, it sets the status of the cursor to be open state. And then when they issue the fetch, what happens is using the plan what was created for the SQL statement, it creates the iterator behind the scene. So the iterator then gets wrapped in an object called cursor result iterator. Why we are to wrap is because, as you remember, in cursor, you should be able to fetch, go through the result set and be able to close the result set, but come back again so that when you do a next fetch, the start of the query has to start from the row what was last read. But in the case of the normal result set, when you close it, the whole thing goes away. So if you have to read back a row, then you need to start from that point onwards. So what we do is we wrap that result at the iterator for the query. So when they do the fetch and then close the cursor, we would not close the iterator, the original iterator, but just respond saying that it's closed. And also, this result iterator would keep track of the number of rows read, because in fetch statement, you can say you want to read 10 rows or 20 rows. So then it goes to the number of rows, keeps track of all the number of rows being read. And then what happens is when the rows are being done, it will say the result set is exhausted, and then the users can do and close. Again, similar to the query processing, what happens is take the cursor result iterator. It also takes the projector object and then wrap it around, and it creates a Phoenix result set and pass back to the client for them to do the iteration. In order to satisfy the prior calls, what we do is as we do the forward or the fetch next calls, we store them, we cache the data so that when the prior call comes, we go back and use the cache to satisfy the prior calls. So that's how the implementation is right now. So one of the initial requirements, as we talked about, we should be able to see a snapshot view of the data. So there's no change being reflected when the users traverse back and forth. By default, in Phoenix, what happens is when a query gets executed, it uses the timestamp of the execution time to be able to pull the data out from HBase. So that way we get free of cost this facility of having a snapshot view of the data. So by wrapping around the result set on a query, we get a snapshot view so that when the users move back and forth, they would not see any other changes happen to that set of data. One of the ideas is like we currently talking about caching the data to satisfy the prior call. But because of the reverse scanning, the scanner being able to be reversible in HBase, for simple queries, which just relies on scanning, what we do is we are trying to use the reverse scanner to be able to whack the forwards instead of scanning instead of caching the data. So if most of the queries are using from your application is simple queries, which doesn't have any aggregation or anything, we should be able to use the walk the scanner in the reverse order to get the data out without caching. Right now, we are having a fixed a parameter or a property in Phoenix, which can be set by the users to cache the amount of data, say 100 rows. It's a number of rows. So what we are trying to do is we are trying to change it to memory based so that you can define the amount of memory you want to allocate for the cursors, so that the projector object we talked about, the size of that size can be calculated from using the size of the projector. We can find the number of rows which has to be cached, and that way it's just much more dynamic. Currently, this is where our implementation is. The fetch next got merged into Phoenix. Fetch prior, because of the reversal of the scanning part, we are having 1 or 2 edge cases we are trying to fix. Once that's done, we are hoping that would get merged as well. so that users of Phoenix can try to use this feature. Again, just to point out all the contributions from the different folks. And as Ani mentioned, that we have Ani's talk tomorrow at PhoenixCon, if you're interested.